Everybody, it's Ripley back again. Excuse me, my voice is a little thrashed today. So today we're going to talk about curl and divergence. And what curl and divergence are operators on vector fields. So think of an operator as like addition, subtraction, multiplication, division, et cetera, et cetera. But this is going to be actually on a vector field. So in other words, if we've got some vector field, f equals pi plus qj plus rk. All right, we played with these ad nauseum for the last few sections. All right, and I want to come up with something called the curl of f. And I'll explain what this is in just a second, but I want to give you the operator first. All right, I'm going to give you these formulas first, and then we'll talk about what they really mean, okay? So the curl of f is defined as, and you're going to freak out a little bit here, this is delta r with respect to y minus delta q with respect to z times I plus delta p with respect to z minus delta r with respect to x time, or not times j, you know what I'm talking about, j plus delta q with respect to x minus delta p with respect to y, and those are partials, of course, k. All right, so let's look at what happens. First and foremost, I have a vector field. I'm plugging that vector, I'm doing this operator defined in this way, and this is what I get. Now, what is this? This is a vector field. So curl, the operator curl, takes vectors, they have to have a vector field, and it spits out vectors. Now, you may look at this thing and you're like, wait a sec, this sort of looks familiar. Now, what the heck is going on here? Well, if I look close, what curl is really defined as is, check this out, if I go I, j, and k, and then I go delta with respect to x, whoops, excuse me, partial with respect to x, partial with respect to y, whoops, partial with respect to y, and you're like, partial what? Well, watch. You'll see, partial with respect to y, and then partial with respect to z, and then I go p, q, r. Look at what this is. It's just a cross product. Well, what is this a cross product of? Well, it's a cross product of the delta operator. Remember this guy back in gradients. We've dealt with gradients a whole bunch, right? I'm actually crossing the gradient operator with what? With f. That's all that it is. That's what curl is. Now look, let me make sure, let's see if you believe me. This would give me, let's change the color of my pen, shall we? Can I do it here? I can't remember. No, I can't. Whoa, what's going on here? Let's go blue. This guy right here is produced by delta r minus delta, or what the hell, partial r with respect to y minus partial q with respect to z. Bam. This guy, how do we do this? Well, j goes partial with respect to, partial r with respect to x minus partial p with respect to z, but I usually subtract that, so I flip them around, right? You see how that works? All right, and then last but not least, where's this guy come from? Partial q with respect to x, partial p with respect to y, subtract those, and I'm there, okay? Now, there's something really interesting here. There's an interesting tool that we get from all of this. If you recall, if I know that f is equal to the gradient of some, now be careful here, of some scalar, right? Remember, I have to have a scalar function here to find a gradient. If I know that f is equal to the gradient of some f, what does that imply about f? Well, we know that that implies that f, the vector field, is conservative. Conservative. Now, I want to show you something that's pretty cool here. If I take the curl of a conservative vector field, what happens? All right. In other words, if I take the curl, oops, whatever, the curl of the gradient of f. In other words, if this is equal to curl, and the way you write this is curl of gradient f, then what happens? What does that turn into? Well, what this is equal to the gradient operator crossed with the gradient of f. And what I end up with is, now I don't want to get too awful with this, but I want you to see it because it's a useful tool. I got ijk, I've got partials with respect to x, partials with respect to y, partials with respect to z. And then I've already got, remember, this part right here, I know that this is the partial, excuse me, the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z, right? F is just defined, f is just some x, y, and z. That's what I'm getting here, right? If I take the curl of that, now remember, this is all, the whole premise of this is that I'm taking the curl of a gradient, which implies this gradient is this vector field, and this vector field is conservative. Well, look close. I get d2f over d, what am I doing? Wait, d2f over dy dz minus d2f over dy dz, right? See what I'm doing here? And then this is going to be I plus, and I'm going to flip them, right? So this is going to end up being d2f over dx dz minus, what am I doing? d2f d2, and I went this way first. So d2f dx dz d2f over dx dz. Look at what's happening. Everything just cancels, right? And then I've got, last but not least, d2f over dx dy. And I know I should be saying partial. I'm being a little bit lazy here. I apologize. Minus d2f over d. And I'm being a little lazy here as well. I should write these as dx dz and dz dx, dy dz, well, I guess, and dz dy, dx dy, and then dy dx like this. But we know by Clairaut that I can flip those around. Everything cancels. And guess what? I get 0. That's pretty cool. So, excuse me, what this really says is if the curl of f equals 0, that implies that f equals the gradient of f. So f, the vector field, equals the gradient of a scalar field, which implies what about f? It implies it's conservative. F is conservative. That's pretty awesome, isn't it? That's that's another really useful tool. Remember, we had the ability, we talked about Green's theorem in terms of being able to tell us whether or not a vector field was conservative. And now we have this idea of curl. Now this gives us another dandy little theorem that says that tells us that the curl of a gradient of f always has to equal 0, right? Because basically, if we have the gradient of f, of this script f, that implies automatically that f is a conservative, capital F is a conservative vector field, and therefore its curl must be 0. Now let's talk about what curl really is in sort of the physics domain. Because mathematically speaking, it's just an operator. It's like addition, subtraction, multiplication, division on a vector. But I got a couple of kind of cool photos here that are pictures that I want to show you. All right, so what curl is exactly the tendency of something to curl in a vector field. In other words, is a vector field making something curl? Now let's go back to kind of the easiest vector field to sort of imagine, and that's water moving down a river. If you were to take a stick and throw it in the river, curl would be at any point in that river would be the tendency of the river using eddies and flow lines and eddy lines and everything that we talked about in class to make that stick curl, to make it spin. And it could spin counterclockwise or it could spin clockwise. If it spins counterclockwise, we know by the right-hand rule and by virtue of the fact that we're crossing that gradient operator with the, excuse me, with the vector itself, or the vector field itself, that it would come up and out. If it were going the other way, if it were going clockwise, the stick rotating in the river, then the curl would go into the water. All right. Now, there's another cool little graphic over here I want to show you. This is pretty. Whoops, that's not what I want. That is what I want. Now check this out. This is really cool. So we have some arbitrary vector field here, and look at, they did a really nice job with this. And we're gonna, when we talk about divergence here in just a sec, we're gonna use this this same thing to describe it. All right, check this out. Notice it says colors show curl. Blue is clockwise, red is counterclockwise. And let's see if we can figure out why that is. Well, look at the vector field. Clearly, if I were to drop a stick right here, what would that stick want to do by virtue of this vector field? It would want to spin clockwise, and thus the curl would go into the plane. Versus the red, look at the vector field. The vector field would make the stick, if I were to drop it right there, it would make the stick want to spin counterclockwise, and thus the curl would come out of the plane at us. Now, we could talk kind of about what would happen here. It looks as though, and notice that it's white, it looks as though if you were to drop the stick here, there would be no curl at all, would there? It would just want to push the stick however it would drop right here, and then it would start to curl here. Likewise, let's see, what's a good one? No, if we were to drop it here, wow, what would happen there? There'd be very little clockwise curl until it got pushed either into one of these guys. Let's see, where would it push it? I guess it would want to push, get stronger, and then start spinning counterclockwise. That's a really cool graphic. We're going to use this graphic again. It's pretty solid. So that's an example, sort of a visual example of what curl really is. You could also talk about particles moving through a vector field or through a gravitational field, and what would happen to those particles as they were affected by the gravitational field. So I hope that's a useful example of curl, sort of in the physical world. Okay, let's talk about something called divergence, okay? So divergence of a vector field of VF. All right, now divergence of a vector field is really simple. It's written as div F. Now this is a vector field. Let's start thinking about our operators here. We know that gradient takes a scalar field and turns it into a vector field. We know that curl takes a vector field and turns it into a different vector field. Now, what divergence does is it actually takes a vector field, and if you look at the notation, it's the partial of P with respect to X plus the partial of Q with respect to Y plus the partial of R with respect to Z. What is this? Notice there are no i's, j's, and k's. So this guy is a scalar. Now, what exactly is that scalar? Well, let's not get ahead of ourselves too quickly here. The way in which we write this, if you look, remember how when if I start with F equals PI plus QJ plus RK. All right, that's my vector field, true. What did I do here? Well, I took the partials of each one of these. Well, we've dealt with partials before in this context. We've done it with gradients, right? Now, I understand that we did it with, I don't want to get too crazy with that, but we started with a scalar field and it spat out a vector field. Excuse me. But what we're doing is we're taking the gradient operator, just the partial operator, and instead of crossing it or doing it on a scalar field, right? We can't do the gradient on a vector field per se because gradient, the operator, is only going to work for us if we do if we do it on a scalar field. However, like before, we can cross it with a vector field, so you might be able to predict what I'm going to do to get divergence. I'm going to dot it with that same vector field. That's all that it is. These are equal, okay? Now, excuse me. We'll talk about what divergence is here in just a sec, but I want to give you another piece of information. Can you think about what the divergence of the curl of F would be? What do you think it would be? What would be your instinct? Well, I'm taking the gradient operator dotted with this guy right here, right? That's what the curl is. I'm dotting it here. Now, let's look close. What do I have here? This is my curl. Now, I can re-go through all this if I had to, but what would happen if I took the gradient of this thing? Okay, so in other words, I'm going to take the partial with respect, to P of X. So this guy right here, right? Excuse me. I'm sorry. I'm taking the partial with respect to this P term, which has now become this with respect to X. So I'm sorry if I'm being a little bit confusing, but you'll see how it plays out here in just a sec. Let's change colors just so I'm not too nutty. I'm taking the partial with respect to X of this guy. right? And then I'm going to add to that the partial. I'm going to try and stuff those in there in just a sec. I'm going to take the partial with respect to y of this guy, and then to that I'm going to add the partial with respect to z of this guy, right? So what is that? I'm just going to leave these parenthetically. Well, what does that give us? It's going to give me partial squared r over partial x partial y, right? Minus partial, those are supposed to be partials, by the way. They're looking more and more like q's, aren't they? Partial squared q over partial x partial z plus partial squared r over partial y, right? Wait a second, where am I? What the heck is going on here? Sorry, you guys. Partial squared p, my eyes got dragged away, partial squared p over partial y partial z minus partial squared r over partial y partial x plus partial squared q over partial z partial x minus partial squared p over partial z partial y. Now, if you look really closely, let's look at what we got here. I've got a yz, partial squared p, yz, or zy, but Claro says that doesn't matter. Those guys cancel. Look at this. That's a partial, dang it. Partial xz, partial zx, Claro, we love that guy. And last but not least, what's this guy? Boom, boom, and I get 0, which is awesome. So we know that the divergence of the curl of f is equal to 0. Irrespective of the vector field, all we need is this vector field with enough partial derivatives, right? I've got to be able to take all the partial derivatives that I need to make this happen. Okay, now, one last thing. Let's talk again. Let's talk about what divergence is in sort of that fluid flow context, okay? And then I'll be done with you. So I love this diagram is absolutely fantastic. So remember this guy where it talked about curl, right? Red is going to have a positive curl where it pops out. Blue is going to have, it's a sink, right? Where you're going to have, I'm sorry, I guess red would be a sink, wouldn't it? You're going to have a positive curl coming out. No, well, I guess I got to think about that. Maybe you guys can help me think about it. I would think by virtue of the fact that the curl is coming out of the plane, that this would be the sink, but it doesn't kind of feel that way, does it? Anyway, you know what? I'm confusing curl and divergence. All right, let's talk about curl, or excuse me, divergence in this case. It says, colors show divergence. Blue is a sink. Oh, yeah. So I was right. Blue is a sink because a curl would be positive here, wouldn't it? Red is a source. So what do you think that divergence means? A strength of divergence. Well, look, red means positive big divergence. Blue means negative big divergence. So what does that mean? Divergence means it's a measure of how much a particle in fluid flow wants to get away from the source. All right? And that's kind of disingenuous. I want to be really careful. What it really means is the tendency of the fluid to diverge from the point, diverge from the source. Now, let me show you another example, and that might clean up that definition a little bit, because I know that's a little bit muddy. Look at this. This is a great one. All right, go away. I don't want that. All right, this is what I want, right here. Now look, whoa. Now look at the divergence here. All right, we've got water. If we think of water passing across the top of a stream, we've got water just sort of uniformly going down. There's no turbulence. There's no crazy going on, nothing crazy going on. All right. The divergence of this is 0. Now let's look at D. The divergence of this is negative 0.36. Now why do you think that is? It's because the strength of the current, as it were, is dissipating. It is diverging, and that can be a little bit confusing. I think B and C are far better examples. This is clearly a positive divergent because you drop a particle in here, that particle is going to want to move away. It is being repulsed. It's being repelled, wrong word, repulsed from the source. This, on the other hand, would have a negative divergence. It wants to pull the particles to it. Now, I know those big brains of yours are thinking about things like electromagnetic forces, force fields, gravitational fields, et cetera, and you would be correct. However, my simple country brain is thinking about this in terms of water, right? We've got something that's pushing water out. We've got something that's sucking water in. But you're right. The applications, excuse me, in electromagnetic fields, excuse me, dealing with particles and gravitational fields, et cetera, they are panoply, which gets us back. Where was that? Let's go back to this. So now hopefully you can see a little bit better what's going on. Now let's look. Why do you think this white has no, this is really fascinating to me. This white has no curl at all. That's something that we can sort of talk about in class, right? Why is there no curl along this eddy line, right? It's kind of like an eddy line. And that's something, well, look at it. We'll play with examples like that in class, because I still have to look at that and be like, wait, why is there no divergence there? I don't think I said curl. If I did, I apologize. Yeah, this is fascinating to me. To me, it looks as though the length of the vectors isn't changing, and it really doesn't want to move. It doesn't know which source it's moving the particle away from if you're caught in this white line. So divergence appears to be a measure from some perspective of a source and a sink. Now, we can explore that some more because, again, the concepts of curl and divergence, while amazing, they can be a little bit confusing, and something crazy might come flying out of my head from time to time. So hopefully you enjoyed that. You've got your equations. Your equations are super simple. And I really like the equations because we get to use this delta, this grad operator, as an actual operator. We cross it, we dot it, instead of just, hey, here's a scalar value. Poof, out pops a vector value. Now we get to understand how it works in context with different scalar valued functions, vector value functions, or vector fields, etc. So thanks for your time and attention. I hope you enjoyed, and I will see you in class tomorrow. Bye.